Hi there. Some time ago I saw this used KENWOOD AC voltmeter model VT-181 on eBay for a good price, and here it is on my bench. It looks to be in quite good shape. But before powering it on, I made it a habit to check the fuses and voltage settings of any device that comes new into the lab. For the selector here, I assume the voltage you can read, that is, it's not upside down or sideways, is the one selected. That would be 220 volts, but the UK has 230 volts, which can rise up to 250, so this setting should be changed. I mean, it's not a big problem, and I assume the previous owner has used this in the UK for ages, but it's less stressful for the unit if the voltage is set correctly. Probing the different tabs inside the fuse holder, I'm trying to find the one with the highest resistance, because that will be the 230 volt transformer winding. Interestingly, in this unit this works without turning the power switch on, because the power switch is actually on the secondary side. Anyway, the highest value I saw was over 300 ohm or so. Inserting the fuse holder with a 230 volts oriented correctly should select it. And measuring across the mains connector confirms that the primary for the largest voltage is now selected. With that done, it's time to power on, although, as I already explained, the transformer is already powered on as soon as you connect the unit to mains. The needle is not quite on zero and the uncalibrated light is on too. The uncalibrated status is because the relative pot was not in the off position. This knob allows you to adjust the needle to a particular value, but of course it means the scale markings are no longer applicable, hence uncalibrated. With that fixed, the zero offset is even more pronounced. Okay, I think the main reason was that it was set to the most sensitive position and picked up noise, changing to 100 mV full scale, and the offset is nearly gone. There are actually two models of the VT-181. The standard one that I have and the VT-181E. The E version differs from mine, that it has a 0.3 mV range as the lowest range, where I have 1 mV. To make up for that extra range, the E model ends at 100 volts while I have an extra 300 volt range. In other words, the ranges on the E version are shifted by 10 decibels downwards. Everything else is the same between both models, except that the E version has slightly more residual noise. Both units have the same 60 dB amplifier. Such an amplifier is handy as it allows connecting other meters, for example true RMS voltmeters, which are by nature limited on how small voltages they can measure accurately. After calibrating the amplifier, it can be used to boost a weak signal to a level they can measure. Let's see how well the meter works. Connecting a 1 volt sinusoidal voltage with a meter set to 3 volts, and yes, the needle is roughly on the 1 of the 3 volt scale. It's not exactly there, so some calibration is probably needed. Turning to 1 volt range, and we have nearly full scale with the needle close to the 10. A closer view of the 1 volt in the 1 volt range. It's sadly not a mirror scale, as for example in my TM3B I showed and calibrated in an earlier video. In the 3 volt range, the needle should be at 1 and is slightly below. There are 3 calibration points. They are accessible from the outside once the 3 rubber plugs and the housing are removed. Sorry for the flicker caused by the interaction of the pulse width modulation of my torchlight and the camera shutter. The top 2 cal positions are trim pots. The lowest one is a trim capacitor. The first cal step requires applying a 300 mV RMS sinusoidal signal at 1 kHz to the VT-181 in the 300 mV range and adjusting VR102 so that the needle is on 3. From my position directly in front of the meter it is, but maybe slightly off for the camera positioned a little sideways. At the same time, the amplifier output needs to be checked with a scope that it doesn't clip. Next, the meter needs to be in the 1 volt range and the 1 kHz input signal needs to be increased to 1 volt. VR102 needs to be adjusted to move the needle to the 10 position. Again, the amplifier output must not be distorted. Lastly, the amplitude of the 1 kHz input needs to be lowered to 0.9 volts, and then the frequency be changed to 100 kHz and trim cap TZ101 adjusted so that the needle again points to 9. And that concludes the calibration. I put stickers on the corresponding color holes, which makes it less likely to adjust the wrong trimmer. These are just temporary. Anyway, let's have a look inside. Lots of screws to open the case, 2 on the side, 4 on top and another 2 on the other side. With that, the U-shaped cover comes off and reveals the inside. The transformer on the rear, a PCB with a shielded section on one side wall, and the instrument and range selector on the front. The enclosure leaves room for another PCB on the other side wall, for example, for a model providing 2 input channels. That is even more likely by the fact that the transformer provides an unused power plug. The transformer provides 2 spare red wires and a black wire, probably an AC output with center tap. There are also 2 blue wires on this socket that go to another plug. This would be a board-to-board interconnect. In my VT-181 none of this is used, but it opens potential for some homebrew add-ons. Let's have a quick look at the schematics. First, the block diagram. Note that this says CH1, presumably channel 1, implying that there is a dual channel version. The circuit is quite straightforward. The input signal goes through an impedance converter and 3 attenuator stages to the main amplifier. From there it branches. One path goes to the meter, which shows the rectified means value. The relative knob allows adjusting the amount of signal going to the instrument. The other branch goes to a second amplifier, which provides the output signal. Below we have the power circuitry. It is clear that the power switch is on the secondary side of the transformer. The AC goes into a power supply, providing ±5 volts to the rest of the circuit. As ever, the actual schematics look more complicated. Starting easy, in the lower right we have the power supply. It's the standard circuit using 2 linear regulators with a couple of smoothing and filtering caps. Directly above is the circuit driving the analog meter. Quite unusually, the whole range switching is actually digital. In the VT-181, the range switch doesn't carry any AC. It just provides DC on-off signal, which are decoded by a bunch of diodes to feed the attenuator circuits on the PCB. This greatly simplifies construction, reducing the likelihood of picking up interference and opens the possibility for auto-ranging or remote control. As indicated in the block diagram, there are 3 attenuators. The first one is this relay that selects between a direct connection to the input for the low voltage ranges and one that first divides it by 1000 for the higher voltage ranges. Another relay after the impedance converter selects between one of 2 signal levels going to an attenuator chain that has 4 taps. Finally, one of these taps is selected using the MC14066 quad analog switch to go to the main amp. Here are those diodes decoding the range switch coming from that connector above. Just to be clear that the VT-181 is an averaging showing meter, not true RMS. Here I feed it a 5 volt RMS signal, but it's a square wave, not sinusoidal. And as any averaging meter, the VT-181 shows a 1.11 times too high value for square waves. 5.5 and a bit volts instead of 5 volts a true RMS meter would show. After calibration, the error at 1 kHz was within 1%, which is certainly better than the max 3% allowed. The bandwidth was also well beyond the specified 1 MHz. But the claimed 5 Hz are not really usable. If you like my videos, don't forget to like and subscribe and help growing this channel, and consider becoming a Patreon. The link's in the description. Thanks for watching.